Welcome everyone. In today's video, we're going to talk about intermediate value theorem. If f is continuous on a closed interval ab, fa is not equal to fp, and k is any number between fa and fb inclusive, then there's at least one number x in interval ab closed such that fx is equal to k. This is an example of existence theorems. Of course, we call these existence theorems. We have another one in this video too, because it's talking about existence of something, right? A value, a function. Let's see. So we have a closed interval AB. A, B. Fa is not equal to Fp, which gives us two options. Fa can be greater than Fp. Fp can be greater than Fa. You can show the one you want, doesn't matter. I'm gonna use this one because without any reason. Fa is here. Fp is here. Let's draw a random function graph as well. Now, k is any number between fa and fb. Let's change the color one more time. So I have a k here, right? And there's at least one number x in the interval ab. So I have an x here. Such that fx is equal to k. So to know what fx is, I need to put the x, I need to plug in the x in my function, right? So my fx is equal to my k. So this is what intermediate value theorem is telling us. You can use fa is greater than fp2. It will be the same thing. I just pick this randomly. It doesn't matter. It will just, the function will be something like this time, and it's going to be the same thing. Verify the intermediate value theorem. In the case of the function fx is given to us, the interval is given to us, and the intermediate value is given to us. To check intermediate value theorem, first of all, we need to make sure that the function given to us is continuous on the interval. Is this function continuous on this interval? How am I gonna answer that is, my function is under the root 16 minus 6 squared, right? And this inside of the root should not be lesser than 0, so the rule is 16 minus 6 squared should be greater or equal to 0. I can write this as 4 minus x times 4 plus x greater or equal to 0. So my roots from here are 4 and negative 4. So let's plug in a value from the right side of the 4. 5, 25, 16 minus 25, negative. Let's pick a value between these. Let's say 3, plug this in. I am seeing that it is positive. And negative 5, for example, again 25, so negative. So in this interval, I am continuous, right? Can we include negative 4 and 4? It can be equal to 0, right, inside the root. So therefore, we can include these values too. The interval we have is negative 4 and 0. So it works completely fine for us. I wish we gave more space. I always do this mistake. Is continuous, right? First step is showing that the function given to us on the closed interval is continuous. The next step is fa should not be equal to fp. We need to see what is fa is equal to and fp is equal to. F negative 4 is equal to 16 minus 16, 0, and f0 is equal to, when I plug it in, 4. All good. And the intermediate value, root 7. The thing is, this root 7 should be between 0 and 4. Is it between 0 and 4? Of course it is, because this is equal to root 16, and of course this is 0, and the root 7 is greater than 0. So therefore, we are getting there. The next step is finding it, right? How am I gonna find it? I will say my FC is equal to root 7, and I need to figure this out So I need to figure the c value, right? So 16 minus c squared is equal to root 7. 16 minus c squared is 7. C squared is 9. C is negative and positive 3. The thing is, I have two values, right? Plus 3, negative 3. Which one to pick, or can I pick both? What can I do? We need to check the interval. Our interval is negative 4 to 0. So therefore, the 3 is not in my interval, so therefore my c is negative 3. And therefore we show that the we can say that we verify the intermediate value theorem, right? Our next theorem, if f is continuous on AB and if fa and fb are non-zero and have opposite signs, then there is at least one solution of the equation fx is equal to 0 in the interval AB. Another nice theorem, another existence theorem. As usual, we need to ask the question, why? Why is this telling us that? How can we come up with that conclusion? If is continuous on AB, again, these functions are non-zero and have the opposite signs. So if I multiply fa and fb, it will be lesser than 0, right? And since these are non-zero, this cannot be equal to 0. There's at least one solution. Why? Because let's say my fa is here and fb is here. Since these are opposite signs, and f is continuous, right? So to go from here, I should draw this line without removing my hand from the paper. I'm not removing the pen, so it can be something like this. So this is telling me that there is a solution, there is a root here. But why is it telling at least one? It's telling at least one because, can I clean this? Because it could be also something like this, right? Maybe it could wave, it could do some waving like this. Maybe we could have more than one zeros. So therefore, fx equal to 0 in the interval AB, we will say at least one solution for if fa times fb is lesser than 0. Show that function fx is equal to 2x cubed minus 4x squared plus 5x minus 4 has a 0 between x1 and x2. First of all, as usual, we will say fx is continuous because why? Because it's a polynomial function, right? So it is continuous everywhere. We can say it's continuous everywhere, so therefore in interval 1, 2 closed, it's also continuous, but we'll keep it short. Next, what is f1? What is f2? f1 is 2 minus 4 plus 5, 2 minus 4 plus 5 minus 4, 2, 7, negative 1. f2 is 16, 4, 16 plus 10 minus 4. These cancel out, so 6. So therefore, f1 times f2 is lesser than 0. Because when I multiply these, I get negative 6, right? So I can say by the intermediate value theorem, we can say the function has a 0 between and x equal to 2.